So let's talk about vector. A vector, first and foremost, is a quantity that has both magnitude and direction, right? So what are some examples? Velocity and force, right? So let's talk about velocity for a minute, right? If you have a quantity which doesn't have a direction, it only has a magnitude, it's called a scalar. So vectors versus scalars. So talking about speed and velocity. If I say that the velocity of an object is 6 meters east, that's a vector quantity, right? Not only do I know how fast something is going, I know the direction. But if I just say the speed is 6 meters per second, that is a scalar quantity because I don't know the direction, I just know how fast. Okay? All right, so take a look at here for a minute. A ball thrown northwest at 60 meters per second. You think that's a vector or a scalar? Vector. A tennis ball served at 110 miles per hour. Scalar. Sprinter running 100 meters north.
No, vector. Yeah, that's vector.
Vector.
Saved himself.
Okay, so vectors, because it's a direction, right? A good way to represent them is using an arrow, okay? We call this an arrow diagram or a directed line segment, okay? So take a look at the vector here. Anything, right, it will have a starting and an ending point, right? There is a starting point and then a direction towards which it's headed. So the starting point has an end point, right? That's called the initial point or the tail, okay? And then there is an arrow to the terminal point or the tip. Tip and tail, or head and tail, it gets a little confusing, right? So to be a little bit more unambiguous, so a little bit less ambiguous, I like to use initial and terminal point, okay? Yeah.
So the tip is the end, while the
tip
is the start?
Yes.
That's backwards.
I know. But think of it as like the tip of an arrow.
Yeah.
Right?
Yeah.
Or if it's a comet, the tail trails the end, right? It's that sort of mentality. So that's why I like initial point and terminal point. Now, how to label a vector? The initial point always gets a capital letter, A, B, C. The terminal points gets a capital letter, A, B, C. To label a vector, you can either use the initial and terminal points, so capital A, capital B, in that order. It's like a ray from geometry. If you do BA, it's going in the wrong direction. And in order to say that it's a vector, you have a one-sided arrow. So it's different from how a ray looks. Or you can give the vector a name with a lowercase symbol. Like I'm going to call this vector A. In that case, you can just call it vector A like this. In print, they also use bold letter A without the arrow on top. But obviously, we can't write that. So, okay. So when we're writing, it's usually one of these two. Yep.
So if this one was, if the initial point was B and the term point was C, would the other way of writing it be like a lowercase b? That's
Oh no, the little a, it's independent of what the
so it's all
initial.
Little a. It's not dependent on what letters.
Yeah, I could have called it like little h. Like it doesn't have to be one of the letters of the terminal and the initial side.
But the capital letter one does.
So I could have another vector that's like this, OT, but I could call it M, right? So.
But then or you could call it capital OT with the arrow.
Right.
Okay.
Yeah. Okay. A vector in standard position is a vector where the initial point is at the origin. So you see here the initial point is at the origin. That is a vector in standard position. Okay? So once you put a vector in standard position, you can talk about the direction. The direction of it, okay, is always the angle between the vector and a horizontal line. So here's how you do it. You have your vector. You draw a horizontal line at the initial point. And then this is angle 0. And so you start rotating to your angle, and this has an angle of 35 degrees. Okay? Let's do another example. Suppose I have a vector that points this way. Okay? I'll call it CD. So what do? Draw a horizontal line at the initial point. Okay? This is 0, right? That's always the 0 degree, right? And then if you move up, you know, let's say this is 150 degrees, that's the direction. Okay? So if I say go 150 degrees from where you are, you know, there is only one place for you to go, because it's like from the horizontal over. The magnitude of the vector is the physical length of the line segment. So if I were to take a ruler and measure this, however many, you know, centimeters, millimeters, inches it is, that's the magnitude. And we give it the symbol absolute value A. Yeah?
Is it not like infinity because it's like an arrow?
Not necessarily. It's an arrow. The arrow only gives it a direction. It doesn't go forever. There's an end point right there.
Oh, cool.
Yeah. Yeah.
And so I see like on the notes it says like 1 centimeter is equivalent to 5 feet.
Okay, hang on. Let me get there. So suppose I took a ruler and I measured that segment. When you measure it, that's 2.6 centimeters. Okay? Now, often a vector can represent something's velocity. If something is traveling with a velocity of 654 meters per second, you're not going to draw a vector that's 654 anything long, right? That's just silly. You're going to scale it down. So for example, in this diagram, suppose you're told that each centimeter represents 5 feet per second. So when I measure it, and this is 2.6 centimeters, the actual magnitude of A is 5 times 2.6, which is 13 feet per second. Okay? Now, this one, bearing, I always think about, okay, should I leave it in? Should I take it out? But I always leave it in for like one of those Jeopardy facts, right? Right? So sailors use, obviously, directions like this all the time, right? Like angular directions. They have like their own way of measuring things, and they call it the direction the bearing. They use like the north, south, east, west. But the way they do it is a little different. So instead of doing the horizontal, I'm just giving you this as like for your information sort of thing. The way they do it, so you can have what is called a quadrant bearing. It's a directional measure, and you can only have a number from 0 to 90, east or west of the north-south line. So how do they do it? They like sailors, right? They always orient themselves according to north, right? So they look at, okay, where is north? This is the north-south line. And now suppose they're going in this direction, right? this is the angle that they choose, right? So this one, look, if this is 145 degrees, this is 35 degrees here. So a sailor would say, I'm traveling 35 degrees east of south, right? That's what they would say, okay? And they see it like this. I don't know if you've seen this, like Navy folk like use this all the time, okay? All right, let's move on to stuff, to this stuff. Don't worry too much about that. Again, it's more like for your information. Okay, vectors. So take a look at this set of vectors here. I just have a couple vectors that I just threw up in the air and they landed as they landed, right? So we've got vectors A through F. Parallel vectors have the same or opposite direction, but not necessarily the same magnitude. Okay, so what are parallel vectors here? Vector A is parallel to vector B, which is parallel to vector C, and also E, and also F. Okay, you see how the lines literally look like they're parallel, but it doesn't matter if they're pointing up or down.
I was gonna say, what about the final arrow, which direction is pointing in? Does that matter?
Right, but so you see how it says they go in the same or the opposite direction? So it doesn't matter.
Right.
Yeah. Mm-hmm.
So what if there were multiple sets that were parallel, but they were parallel, like they weren't all parallel in like the same way? Like how would you separate the groups?
So you're never going to be given a set of vectors and say, like, choose the parallel ones. But if they, like, I'm just like defining terms. But if that came up, you would just say, and, like, E is parallel to H or whatever. Now, equivalent vectors have the same magnitude and the same direction. So they literally have to be clones of one another. A and C are equivalent vectors. And the way I say that is A is equal to C. If you drop the arrow, it will be points off, just like in geometry. If you didn't put the line symbol or the ray symbol, right? Opposite vectors have the exact same magnitude, but the opposite direction. So here, look at vector E and A, right? So I say vector E is the negative of vector A. And yes, E and C have the same relationship, okay?
Wait, but
No.
so why did this not have arrows on it?
Because it's bold, right?
Oh.
If it's bold, right, then it takes the place of the, and I purposely put it that way because I want more exposure.
So it's negative A?
Yeah, E is equal to negative A. It means E and A have the same size, but they go in opposite directions. Yep, it is cool actually. So in the world of vectors, the negative, its sole purpose, right, is to denote direction. Okay. All right. Resultant vectors. So resultant vectors are basically the sum of two vectors. Okay? Your whole life you've been dealing with real numbers. 1, 2, 5, -7, I, or like A, C, D, whatever, right? Those are numbers and you apply operations to them. A number plus a number is another number. And we call it a sum, right? Vectors are different beings, okay? They're a different species almost. So their operations are different. Their realm and their world is different. When you add two vectors, you call the result the resultant, okay? And they add a little differently. So, how do we add them? There is more than one way. I like this triangle method the most. Okay. Remember, vectors always represent like a direction of something. Pretend vectors represent a route, okay? What you do to add two vectors is this. So here you have two vectors, A and B. You're going to add them. Do you see how A goes in one direction, B goes in another direction? Pretend those are two routes that a person is walking, okay? The resultant would be the net change of where the person was at the beginning and where they ended up. So what you want to do is you want to combine the vectors, right? So that A and B are a continuous route, right? So look, you take A and then you literally grab onto B and you put it here, but in this direction. So if you trace it, it's like a one-way route like we have on campus now. So if you trace this, you would have, go to the arrow side and then continue through the arrow. Does that make sense? So you wouldn't do it this way. You wouldn't have two arrows this way, right? Because now if you're going along the purple, then you can't, it's the opposite way for the blue. Does that make sense? Okay. Now, where was the starting point? Here. Where was the ending point? Here. The third step is you draw a line from the starting point to the ending point, and this is the resultant. Okay?
Which direction?
Oh, it goes here. It goes from the beginning to the end. So it has to go that way. So let's do one here. I have V and W, which I need to add. Okay, so we're going to start with V. So what we're going to do is we're going to reproduce V here. Okay, be as precise as you can.
And this is not like A squared plus B squared.
No.
Right?
No, not at all.
Matthew.
Okay, so that's V. Maybe it's a little bit shorter. Okay, now on top of this, I'm going to connect W to this. But W should only connect this way, right? So you have a continuous motion of flow. Now, where was the start? Here. Where was the end? Here. You draw a third arrow from the very beginning to the very end. And the direction has to be, from where you started to where you ended. That is now the resultant V plus W. Okay, questions? Yep.
So that's our answer.
That's
we don't
your-
have different colors, so.
Yeah, it's fine. You don't need different
It's fine,
colors.
okay.
Yeah.
So there's no actual map.
Yet.
You just wait. You think this is easy? Just setup.
I know I didn't.
There are 2 more pages to note.
Take a look at this one. I have A and I have negative A. Those are the two vectors that I'm going to add. So look at A. I'm not going to redraw it. I'm just going to leave it there, and I'm going to draw negative A on top of that, right? So that's the first vector, the blue one, A. Now, it starts here, right?
Oh.
The other one, negative A, you started where the first one left off. This is where the first one left off. So I'm going to draw this, right? Negative A, right? So where is my ending point? Here. So if I were to connect the start to the end, what would I get?
The middle. Oh my god. Wait.
You would get the end.
You would get 0,
Yeah, but you didn't say
right?
Wait, I'm so confused. Why can you just change A to negative A?
No, I didn't change A to negative A. So
But, then what is? Then
I'm going to combine.
Whoa, that's like a combustion. Oh my
I'm going to combine the two vectors. This was A, right?
Now there's a negative A.
Sorry, this was A. And now I'm going to take the second vector, but I'm going to draw it starting where this one left off, right?
Oh, you just drew it on top of it.
You just do it on top of it. It's 0 because you
go
just,
there and back.
you go there and back.
Yeah.
So A plus negative A is 0.
That's pretty cool.
Okay, yep, it is. So take a look at this one. You have a vector that goes 25 newtons north. So let's just draw that. 25 newtons north. Right? So, okay. 25 newtons north. And then 35 newtons south. So I'll do that one in another color, green, red. So from here, now you're going to go 35 newtons south.
Oh my god.
Where was the start? Here.
It's -10?
Yeah.
Wait, no. Wait.
So from the start to the end is 10 newtons, negative 10 newtons.
You did the.
Okay, so let's do that again.
Yeah.
25 newtons north.
That one clicked.
Alright, now again.
Here's where we left off. Now I'm going to do, from where I left off, I'm going to draw 35 newtons south. Here. So now if I go from the very beginning to the very end, it's negative 10.
That one clicked.
Mm-hmm.
That's a good one.
Nice job.
Yep.
I went to lick my finger for my page.
Okay, multiplying a vector by a scalar. If you multiply a vector by a scalar, by a regular number, all you do is just literally scale the vector. So if I have A, and if I multiply it by 3, now I have 3A. You literally scale the vector, so now it's 3 times as big. Okay?
Oh, because it's just the speed.
You
so it's
literally-
Just the number. It's just the number.
It's literally a scalar. It is a number that scales the vector. Boom, boom, boom.
So you'll just be given a number.
Yeah.
So sorry. Can you, wait.
We're going to do more. Sydney.
The problem.
Sydney, let's do more. Okay.
Oh no, Cindy, here's the math.
So take a look at this. I'm given X and Y. Now I need to draw 3X
Yeah.
minus 3/4 Y.
Yeah.
Okay, so look.
I'm tapping out.
No, this is
Okay,
fine.
look. This is X. 3X is a vector in the same direction, but 3 times bigger.
Oh.
And then 3/4.
Okay, now look. Look. This is Y. 3/4 Y is this big. But I don't want 3/4 Y.
You want me?
I want negative 3/4 Y. So from where this ended,
Oh my.
I go in the opposite direction.
That's math.
But look, you know what I have so far? This is not 3X minus 3/4 Y. This is just 2 random arrows.
Oh no.
Because this
Don't do it.
is a sum or a resultant. To get a sum or a resultant, the real answer, the result, is that final arrow from the very beginning to the very end. Now that in green, this is 3X minus 3/4 Y.
That's a hoop.
That's funny.
Uh-huh.
Like at first, the negative with the 3/4 Y was throwing me off, but then I
Yeah.
remembered that it's the direct. Oh my god.
Yup.
So then ultimately, yeah, you get your equation of 3x.
Yup.
Wow, that's something.
Okay.
This is math I love.
Vector we haven't even done anything with vectors yet.
Wait, hold on, what?
I don't like doing it.
Okay.
Maybe it's not.
Vector components. Okay. All right. Vectors which add to create a vector R are called its components. So look at this configuration here. The red and the blue added to create the green. So the red and the blue are components of the green. So now, if I had a vector, I can actually come up with its components. I can draw two vectors that combine to give me that green one, right? Yeah, but is there another possibility?
Yeah, because they're negative and positive, no?
Look at this one. Yeah? Look at this one. Look at how many different ways that two vectors can create that red one,
How many?
that green one. Wait. We're not, okay. All the things I'm telling you right now are all just information. You're never going to be asked anything like this. Okay? What I'm telling you are just the basics now, the building blocks. So now, there are an infinite number of possibilities.
Yeah.
But there is one pair of vectors that are the VIP among the infinite possibilities. Because you know what? Somebody else might come here and do a mic drop. Somebody else might come and be like, look, I can do a purely horizontal one, and I can do a purely vertical one and create a right triangle. Okay? These ones are called, that pair is called the rectangular components because they form half of a rectangle. So, moral of the story, infinite pairs of vectors create a resultant. But that pair, right, which is horizontal and vertical, are called the rectangular components. What I just did here is I resolved a vector into its rectangular components. Because now I have a vector x and I have a vector y, and that's what I did. So give me 1 second here. Okay. I just want to share here. Okay. All right. So while digging in his garden, Will pushes a shovel. So this is the stuff that you're really going to need to know. Will pushes a shovel into the ground with a force of 630 newtons at an angle of 70 degrees with the ground. Okay? Draw a diagram that shows the resolution of the force that Will exerts into its rectangular components. Okay. Let's draw one. Okay, so first let's draw. Okay, so picture somebody like, just holding a shovel to the ground, right? There is force being exerted from your arm to the ground, and that force is traveling through that shovel, right? So if this is the ground, this is the shovel, and it creates an angle of 70 degrees. Okay? So now, what you want to do is the following. Is all this. Okay. So now you want to draw the vertical components of this, right? So the vertical components are the following. God. Okay. So you have one arrow that goes down and another arrow that goes across. Okay? Look at the arrows. The arrows will represent the direction of the force. So the force is going in this direction, right? Starting here, ending here. If you follow the other pair of blue and green, it should follow the same direction. Boom, boom. You see that? So that's how you know that your arrows are oriented properly. Okay, so now let's label this. This is the force, and it is 630 newtons. This is the X component. This is the Y component. That's what you need if you want credit for this. If not, just do what you want. Okay? All right.
Do we have to write start and end?
No. Find the magnitudes of the horizontal and vertical components of the force. How big is this? How big is that? Right? Okay. Yes, it's a right triangle. But we can't do a squared plus b squared because you don't have all the things. So trig it is. Okay.
Sine and cosine type stuff.
So here's y. Here's x. And then this is 630 newtons. Okay? All right. This is 70. So let's do x first. Okay. Cosine of 70 is the magnitude of x over 630. So when I multiply both sides by 630, x is 630 cosine 70. Yes, you have to be in degrees. So x is 215.5 newtons.
What, like, the absolute value signs, like,
Means magnitude.
Means magnitude, okay, perfect.
Okay, y. Sine of 70 is the magnitude of y over 630. Multiply both sides by 630. So y is 630 sine of 70. So y is 592 newtons.
We can use calculators for this.
Yeah. Okay.
What should we round to? 10?
Usually, I'll specify on tests, but usually 10. Okay. So, get used to this line, because it's always going to look like that. Remember when I taught trig, I always said x was associated with the cosine and y was associated with the sine. There is a reason why I sort of force that stuff on you. It's because it shows up again here. And you have to know that x and cosine are together, the vertical and the sine are together. Okay. Here we go. A player kicks a soccer ball so it leaves the ground with a velocity of 44 feet per second at an angle of 33 degrees with the ground. You will never watch soccer the same way again, right? Draw a diagram that shows the resolution. Okay, so here is the guy, soccer player, 44 feet per second. This is the velocity. Okay. X component, Y component. So look, suppose I have my arrow for the blue going that way. Nope, that doesn't work. Because so there are two routes. One is the purple, and the other is the pair of blue and red, right? Look at the blue and red. That's like a dead end. So I have to have it oriented this way. So this is Y, and this is X. Okay, find the magnitude, right? Let's do x first. Okay, x is always the hypotenuse times cosine of the angle. You don't believe me? Do it the other way, right? Cosine of 33 is equal to blah over blah. So this is 36.9 feet per second. Y is the hypotenuse times the sine of the angle, 24.0 feet per second. Okay.
I don't know why the y is going up. Because you're finding like where it is in space, not where it's landing.
No, you're finding that this has nothing to do with where the ball is per se. this has to do with this, diagonal arrow, right? It's going this way. So the ball came from here to here.
Yeah.
That's one route. Or follow the route without taking off your pencil this way.
Yeah.
So now that we made that start to end.
Now, here it is. When you talk about vectors, V is the resultant vector, which you get when you add the components. Okay? But now, look at the numbers here. Look at how the world of vectors is different. Addition in vectors is different than addition of numbers. If you straight add x and y magnitudes, 36 plus 24, does that equal 44? No, right? So it's not straight addition. So vector addition is a little different.
Whack.
Okay? Okay? All right. So I will end here. So your homework, which is on the lesson plan, is actually current. It was meant for all this to be covered in one day. I just forgot to take it out of the thing. So with that, I will end my screencast.
Have a great weekend.
1 second.